So when n is not large enough, there is still something that we can say. There's something that we can say for any n. Even when n is equal to 2, we can actually say something. Of course, it's not going to be a very strong statement, but we can say something. So there's this result called Hoeffding's inequality. Date back to the 60s. Running horse, not only of statistics, but actually many randomized algorithms in computer science, machine learning. Hoeffding's inequality is an extremely important quantity. If you ever write a paper on, say, theoretical machine learning, chances are you're going to be using Hoeffding's inequality. So I'm not going to spend too much time because we're not going to use it, but I just want to tell you that there are some tools out there that are useful even when n is finite. And the research trend these days is to make finite sample statements, not as n goes to infinity, but for finite n. And so these are the tools of choice. So what does it say? Well, it's not going to be as general as the central limit theorem, but it's essentially delivering the same message that xn bar minus mu is xn bar is close to mu at some deviations that are of order 1 over square root of sample size. Okay? And this is how it goes. First of all, you have to make restrictions on the random variables that you're using. When I use the central limit theorem, I basically assume that I had a mean and a variance, and that's all I needed. Here, I actually need much more. I need that my random variables are actually almost surely bounded. Okay, so for example, this rules out Gaussians. This rules out exponential random variables. Everything that can take values that are arbitrarily large or arbitrarily small, by small I mean far in the negative infinite, are going to be ruled out. But if you have, for example, random variables that take value in the interval 2, 3, all of them, you're good to go. Can somebody give me an example of a random variable that takes values in a bounded interval almost surely? Yes. Bernoulli, right? So Bernoulli take value either 0, 1, which certainly is in the interval 0, 1. Okay, so this is the main constraint. But once you have this, you actually can make a statement about the probability that xn bar deviates from mu by more than epsilon. And the bound that you get is this slightly complicated form. We're going to just parse it a little bit. But what's nice is that this thing decays exponentially with n. Exponentially fast. All right, so if I start having, even for moderate sample size, if n is equal to 20, you get e to the minus 2 times 20 times epsilon squared. Okay? But let's see what makes this thing start to kick in, right? For this to actually hold, n needs to be large, but epsilon needs to not be too small. And in particular, if epsilon squared is like 1 over n, then these things cancel out, and there's nothing that's happening. And when is epsilon squared equal to 1 over n? Precisely when epsilon is 1 over square root of n. So if I were to stick in something which was, say, a over, well, not a, I used it, but say c over square root of n, then I would actually cancel the n out, and I would have e to the minus 2c divided by b minus a squared. So in the Bernoulli case, forget about the denominator. So we would have something like, so if, let's say, xi's are IID Bernoulli p, then that would tell me that the probability that xn bar minus mu larger than c over square root of n would be at most 2 times e to the minus, well, see, if epsilon is c over square root of n, I'm going to get n times c squared divided by n. So I'm going to get only the c squared that stays there. So 2c squared. And then b minus a is equal to 1 in this case, okay? So that's what I get. So I get something which is, in a way, the same kind of like quantity that's for c large enough, it's going to behave essentially like a Gaussian, okay? But the main result tells us that this square root of n order of magnitude is true for all n's. Now, if you want the precise constant here that comes from the Gaussian, you have to use the central limit theorem, which is a limit statement that holds for large enough sample sizes. But the square root of n qualitative behavior happens at any n. Okay? So the conclusion is the average is a good replacement for the expectation. And now we not only know that the law of large number guarantees that, but we also know that Hoeffding's inequality guarantees that for all n. Okay? Are there any questions that you could ask? Yes? I'm sorry, I can't hear you. Can you? It should be what? Chebyshev inequality, yes. Yeah, so Chebyshev inequality is essentially similar, except that it requires less conditions. So it does not require that the random variables are bounded. But you're not going to get the exponential behavior if you have Chebyshev's inequality. If you have Chebyshev's inequality, what you're going to get is the variance of xi divided by epsilon squared. Sorry, the variance of xn bar divided by epsilon squared. And so you're not going to get this like exponential decay with n. So yeah, I had a question that I wanted you to ask, and now I forgot. What is it? Yeah, so you may ask, is this tight, right? That's the annoying thing about inequalities. When I write the statement like this converges to a Gaussian, then I know it converges to a Gaussian and nothing bigger than a Gaussian, smaller than a Gaussian, much smaller than a Gaussian. Inequalities, I just said that this is less than this. This could actually be e to the minus exponential of n, right? It could be much, much smaller than that. I don't know. I'm just giving you an inequality, and so it could be tight or it could be very loose. This one is actually tight. So if you actually plug in Bernoulli's and you compute this thing and you're looking at something of the form e to the minus something, then what you're going to get is precisely this bound. Okay? So if you're not looking, so there's functions that are slightly more precise, but they're just more complicated. If you want something that looks simple, like e to the minus something, this is what you're going to get if you use Bernoulli's. Okay? Okay, so this is essentially a recap of what I've been saying out loud, but we'll just like, see what are the immediate consequences we get for, say, the KISS example. So the first thing is that in the KISS example, when I have Rn bar, remember that was the average or the proportion of people that turn their head to the right. We know that this thing actually converges weak and strongly to P. And P being the parameter that we're interested in, P is the actual proportion of people throughout the entire world who turn their head to the right. So the law of large number tells us that this is converging. What we say is that this is a consistent estimator. Okay? Consistent just means that the estimator, Rn bar, converges for large enough sample size to what we're actually trying to estimate. So it sounds like a pretty desirable property. Okay, so let's try to always have consistent estimators. One of the typical questions you get when you devise an estimator, the first question I will typically ask you is this a consistent estimator? And typically, the way you prove this is by using the law of large numbers. There's a little question here. What modeling assumptions did we use here? Anybody can tell me? Yes. Yeah, so we use the fact that they're IID. And actually, in IID, there's two hidden assumptions. The first one is I, and the second one is ID. And so, oops. So IID, let's write it like this. So sure, they're independent. That's the first assumption. And the second one is that they're identically distributed. When they're Bernoulli, that just means that xi follows Bernoulli pi, but all the pi's are equal to p. Okay, so that's what ID means. Identically distributed, everybody shares the same parameter. Okay? Now, as I said, the central limit theorem, which I will mostly actually probably always write CLT from now on, refines this by telling you how good it is. So it's going to tell us something of the form, it's actually not just consistent, but it's something that stays pretty close to the quantity you're actually trying to get. And the order of magnitude of the deviation is 1 over square root of n. So let's work this out a little bit. So for example, if I'm interested in the probability that Rn bar deviates from P by more than epsilon, right? That's a very natural question you may ask about your estimator. So we know that by the central limit theorem, this is approximately equal to some Gaussian. So I need to just check which Gaussian this is. Okay, so how do we do this? Well, let's just do it on the board. So I know that Rn bar minus the expectation of Rn bar, which is P, divided by the variance of the Bernoulli, which is P1 minus P, times square root of n, converges in distribution to some standard Gaussian, right? And that's just the central limit theorem. Everybody agrees with this? So now I want to sort of replace this thing with some approximately equal. Okay, so I'm just going to replace this with some approximately equal, and that's the approximately equal that you have. By this, I mean the sample size is large enough so that the central limit theorem holds. So n is larger than 30. So that means that what I really want to understand is the distribution of Rn bar minus p, not just with all this thing around. So what is the approximate distribution of Rn bar minus p? What is the mean? So all I have to do is to multiply both sides of this twiddle equality by p1 minus p divided by square root of n, right? So the mean, the way the mean is going to be affected, I'm going to get, well, 0 times this quantity, so I still get 0. And what is going to be the variance? Oh, sorry, there's a square root here, I'm sorry. This was square root of the variance, right? What is going to be the variance I get on the other side? np1 minus p? p1 minus p divided by n, right? I multiply, so I have to flip those two guys, right? And then square them because they're appearing in the variance. We'll come back to those rules about Gaussians if you're a little lost about what's happening when I start multiplying Gaussians. But the rule is, if I multiply a Gaussian by a number, then it's if its mean is multiplied by this number and its variance is multiplied by square of this number. Okay, so here the number that we used was square root of p1 minus p divided by square root of n. So this is telling us that this is approximately what we want. And so the probability that that Rn bar minus p exceeds epsilon, well, it's approximately equal to the probability that some Gaussian does this. Okay? So here, what I need to write to complete this slide is just p1 minus p over n. Okay? So again, this little twiddle here relies on the central limit theorem. I need n to be larger than, let's say, n larger than or equal to 30 to have the central limit theorem that holds. So in the KISS example, I could ask, okay, so here I still have a bunch of different things. So in the KISS example, what would happen is that if I look at, so I don't know exactly what this p is, so I need to estimate it. But if you actually start to find some epsilon so that this probability here is approximately equal to 5%, right? Let's say I want to find a number, epsilon, such that the probability that xn bar, that Rn bar deviates from p by more than epsilon is at most 5%. Okay? That's the one where you're not too overwhelmed. You're whelmed. Okay, so now if you look for this number, what you get is 0.84. So we'll go back to how to find this number when we talk about confidence intervals, because there's a little bit of things that's unresolved is the fact that we actually don't know p. If I wanted to compute this probability, that would be a little difficult. But we could look at worst case. We could solve some equations. We could plug in some estimator. There's several ways to actually go around this. We'll come back to it. But this is really the way you want to use this result. You first set what the right-hand side should be, and then you find actually what is the constant that you're getting. Okay? And here I plugged in the fact that, so this already factors in the 1 over square root of n, right? I had a 1 over square root of 124 showing up in here. Okay? So this is how we use the central limit theorem. Now, as I said, this requires n to be larger than 30. So how would we go about solving this problem when n is not larger than 30? Let's say n is equal to 15. Well, we still have Hoeffding's inequality. Hoeffding's inequality will not give us a thing that's like approximately equal to 5%, but it will give us something which is less than or equal to, right? And that's essentially how we use this. So let's just look quickly at what, let's go back to Hoeffding's inequality for 1 second. It says that the probability of Rn bar minus p exceeds epsilon is bounded by this quantity. So let's just plug it in. So here we're going to get the probability that I exceed this number. So this number here is just the number that I found so that I would get 5% in the first place right here, okay? And so the number I'm going to get is 2 times exponential minus, what was it, 2 times 124, which is my n, times epsilon squared, which is 0.084 squared, divided by 1, right? That was 1 minus 0 squared, because the Bernoullis are, so let's just write it as 1 minus 0 squared. We have random variables that are in the interval 0, 1. That's what Hoeffding's inequality tells us. And you compute this number, and what you're going to get is something like 0.347, okay? Which I'm going to round to 0.35. So let's parse this for a second. If I use Hoeffding's inequality, it tells me that the probability that I deviate from p by more than this number is about 35% at most. Could be much better, but it's at most 35%, and that's for sure. Okay, so that's nice. The problem is 35%. I'm not overwhelmed. I'm not whelmed. I'm actually not impressed at all, right? I mean, if you tell me that, yeah, you know, a third of the time this is going to be a good interval, but you know, sorry, a third of the time it's going to be a bad interval, but 2/3 of the time it's a good one. So you know that depends on what you're willing to live with. So you can see the difference. Here we went from 5%, meaning we're actually pretty sure that the margin of this happening is actually pretty small. 5% is a pretty tolerable number, but 35% is actually kind of bigger. So Hoeffding's inequality is certainly more conservative. That's what we say. We say that Hoeffding's inequality is more conservative than the central limit theorem, but it's also less precise. Okay? And that's why people, if you go across Main Street in biotech and see people doing market research, drug testing, all these things, they're not going to use Hoeffding's inequality. No one wants to do this because with the same amount of data, you actually make less precise statements than if you were to use the central limit theorem. Okay, so people prefer to rely on more precise statements. Any questions? Okay, so let's move on.